Okay, hope you'll be able to see the screen soon. Okay, we are solving these issues. I can say a few words about myself. There was a very long introduction before. Okay, I think what need I do? I need to do this type of thing. Yes. Okay, so yes, I'm leading a laboratory in Russia. And I'm a visiting professor at Beijing. This BIMSA is founded by Tsinghua University. I suppose you're aware of Tsinghua University. It's the biggest one in China. And also a few words about myself. Yes, it was mentioned that I have a research group and I publish at top venues and so on and so on. So, okay, and if you want to join my lab, okay, you can come after the talk and we will discuss this. Also, I develop not only fundamentals science issues. Like
take it closer to your mouth.
Closer? Okay. I need to turn it. Okay, is it good now? Okay. So what also I'm doing, doing his industrial projects, good ones, and so on. Today, actually, we are going to talk about hallucination detection in large language models. And actually, this will be kind of long talk, so I would be happy to include many details in it. Not only practical engineering approaches to detect hallucinations, but also discuss the core ideas behind the hallucination detection problem. Specifically, I will talk about uncertainty estimation in machine learning and in deep learning. How can we say how confident in the answer provided by the model? But right now, let's put it simple. Let's start with very informal discussion what's hallucinations, and we go back to uncertainty and so on. Also about questions about technical level of the talk. Questions are welcome. I suppose if you don't understand something and you have a question, you are not alone in this room that don't understand something. Also regarding the technical level, it varies during the presentation, has a lot of formulas in some parts. So if you're completely lost and don't have this kind of courses right now at your undergraduate study, it's okay. I hope you will survive to the next part that would be more informal. Okay, so all preliminaries told, and I can start finally the main part of the talk. So I would like to say that I suppose hallucination is a pretty common thing in LLMs. I would also say it is not like a very precise term. Rather, I would say that we can refer as hallucinations some errors that LLM produce. So we have some input, maybe multimodal input with a text and an image, maybe just a text, ask a question, and then we have a response by some model, some LLM, and sometimes this response is not something we expect, something wrong. And okay, because we're asking this question, we don't know the answer. And so there is a risk that we use this answer to make some bad decisions, especially given that we ate some not very healthy mushroom this time. So the question appears, how should we handle this? And actually in this talk I would try to cover two topics on this. The first one is to construct a detector. So a model says how confident it is about its answer. And sometimes, if it is not confident, we just can say, okay, I am not certain, please provide more information, and I will try to repeat the reasoning, repeat the thinking, and give you the right answer to that. Another option, okay, would be to have a better model and that, okay, doesn't hallucinate that much, and we'll discuss this also as well. Also, inside hallucination detection, we can think about different types of hallucinations. Let us again consider some example. So a user asks about a recipe for a dinner. And we see LLM response. Yes, here is a delicious recipe for lunch. So how about fried chicken with mashed potatoes? In addition, tomatoes are also an excellent parent for this dish as they are rich in calcium. Enjoy this steak. As you can see, there are many errors, many hallucinations in this response. For example, we have a request from user to have a recipe for dinner, but LLM decides, okay, it's now at lunchtime, so please use my lunch recipe. So it's the conflict with the input. In a way, it's kind of easier to spot, but anyway, it appears kind of. I spend a kind of very clear example of hallucination, of breaking the facts we present in the model. Another thing can be context conflicting. In this case, LLM generates a long text, and if it generates a long text, maybe in this text there would be some conflicts inside, some errors. For example, there was a recipe for fried chicken, and in the end, LLM, for some reason, decides that, okay, you should enjoy the steak, not this fried chicken you cooked. Maybe kind of you failed at it, and instead you ordered a steak. But anyway, I suppose from the context, it's clear that there is some conflict and there is another error produced by LLM. The third thing is that sometimes LLM needs to use some outside fact, some outside common knowledge. Right? What is the capital of Nepal, and so on. And in this case, we also see that LLM gets it wrong, because actually tomatoes are not that rich in calcium. So, again, hallucination, again, a different type of it. There are some other types, and okay, if you want to explore this more, I suggest you to read this article. Also, an important comment here is that typically, I would not say that this simple question would be so tricky for LLM. Typically, we obtain a pretty good answer with pretty high accuracy in terms of kind of all these facts, and actually they are kind of close to humans in their performance in many aspects. The problem still exists about kind of some narrow knowledge, some long context, and so on. We'll discuss this a bit later, but I would say that kind of in a regular life, we kind of can live pretty safely with the advices an LLM gives us. But if you need some complex output, if you need some complex planning, or if you need some safety critical applications like medicine, unavoidable, you kind of come to guardrails, to some way to detect hallucinations and to fight them, to make them work. And if you are going deep into the theory, you can say, okay, the hallucinations are unavoidable. And again, it's very common for all machine learning systems. All machine learning systems make errors. And so now we want to go through another problem that's very close to this one, uncertainty estimation. So in general, when we are thinking about something like this, about hallucination, we are thinking about that a model has errors in its output. And we have the similar thing for common machine learning models. For example, models for fraud prediction, models for client scoring, model for kind of detection on cancer on images, and so on. And overall, we have this issue that sometimes model has errors, and we want to find or at least estimate the probability of this error. Overall, I would say that, okay, we are also living kind of uncertain life, and we don't know everything in advance. Sometimes it's because of lack of knowledge, sometimes because of lack of something else. But overall, we can define the uncertainty. It's a situation when we have imperfect or known information, or a model doesn't know something. And okay, it's very natural desire to quantify how big this gap, how uncertain we about the output of the model. And we can say this about ourselves as humans. Okay, should we take an umbrella outside? Would it be a rain today? Or if you are referring to an output of an LLM or another machine learning model. And would like to share some examples of why uncertainty estimation is not only some important fundamental concept in the ethics of AI, in the reliability of AI, but also something you can easily apply in different problems. The first work is something I did with kind of quantifying uncertainty of blood sampling. So you see some images of blood sampling on the top right corner, and sometimes this image is not enough to quantify the specific blood type. And the question of this research was, can we from this image say that this image is not good enough, or in other words, that the model is uncertain about it. Not only the model, but also it can be a human who is uncertain, who sees this image and says we need to retake the blood test. And this uncertainty is kind of perfect way to say that we should do test the second time, that the quality of an image is not good enough. Another kind of canonical application of uncertainty estimation usage in machine learning is active learning. Who knows what is active learning? Okay, nice. Okay, I will explain it in a few words. So, a typical scenario in machine learning is when you have some examples and you have labels for examples. For example, you have a sample of frauds, you have a sample of healthy and unhealthy patients and corresponding data for them, and so on. But typically these labels don't appear out of nowhere. Each label costs some money or some efforts or some other resources or time of some medical expert. And so instead of labeling everything, we can try to focus on labeling essential examples. So out of, I don't know, 10,000 patients, you select 200 or 400 patients, label images for them, and train the model only for these labeled images because you have budget only for labeling 400 images instead of all the images. And so the question appears, if you have a big samples of possible labels, of possible objects, what you should label? And it's not an easy question to answer, but uncertainty provides one possible answer to it. We can say, okay, we have some initial random labeled samples. We constructed a model using these samples, like 100 examples. It has some quality, but it is not sufficient to use in production, to use in medicine decision making. So we need to select from all other applicants, for all the patients, the most important part of information that we would benefit the most from labeling. And uncertainty provides, again, a very reasonable answer to this question. If the model is uncertain about some example, it typically would mean that we need to label it because it would help the model to acquire new knowledge, to make it more knowledgeable of something they don't know. So uncertainty is a signal about the absence of knowledge of a model, and so a good signal for active learning, for human annotator to annotate these specific examples. And finally, we can say, okay, hallucinations in LLMs also about uncertainty. If we have a prompt, a response of a model, and we can say that there is a high probability of an error, a high probability of hallucination, it also can be interpreted as that we are uncertain about the output, that the model generated something, but it is not certain if it is good answer or not. Okay, so you can see that there are some very crucial examples related to uncertainty estimation, but also let us provide some for you other example. Okay, sorry, I can try to make it more reliable. Okay. So also one issue with uncertainty is that it can be of different types, and different types of uncertainty are useful in different ways. Let us imagine that we have like this blue cycles and red triangles. Blue cycles are images of dogs, red triangles are images of cats. And so we want to create a classifier that separates blue cycles and red triangles. So it separates cats from dogs, images of cats and dogs. And okay, there can be some images in the middle. And we would be very uncertain about these examples. So we have this something in the middle between a cat and a dog. And it means that the data itself carries a lot of uncertainty. It means that the data is uncertain by nature. We can't make a model better. Whatever good model we make, it is still somewhere between a cat and a dog. It would still say, okay, the probability of this image to be a cat is 0.5, and for a dog, still 0.5. It means data uncertainty. Also, we can refer to another type of uncertainty, model uncertainty. So again, the same problem, dogs, cats, blue cycles, red triangles. But now we feel that for some examples, the model is not good, not because that the example itself is bad, but rather because the model is bad. It lacks the knowledge about the specific example. So these are not very typical dog, not a very typical cat. It is not the training data, and we can make it better. Yes, if we add these examples to a training sample of this species, then we retrain the model, we obtain a better model that has reduced model uncertainty. So if you are talking about some regression problem, we also can say something about this model and data uncertainty. So again, also kind of toy example, but a bit different one. So we have like an input variable x here as this axis. We have an output variable y as this axis. And our training data is this blue dots. It means that it has some input variable, corresponding output variable, and we have two clusters of points here and here. And what we can say again about model uncertainty and data uncertainty here. Here we see that the observations are pretty noisy. Yes, kind of a big spread of points of these blue points, not very well, kind of corresponding to this strict line, the true model. On the other side, there is a data cluster with low data uncertainty, because here you have kind of very small amount of noise. We are very close to this line all the time. So we can say that we can quantify high and low data uncertainty in this way for regression problem when we want to predict the target variable y given the input x. Also, we can say that as this image, we have parts where we have high model uncertainty, and it means the absence of the training data. Yes, in these yellow regions, we have no points, and we actually don't know what this function will be. Maybe it would be something like this, yes? Maybe it would be something like this. Okay, we can make some educated guess, but still we would be very uncertain about what the model should answer here. And if we are returning back to our kind of applied problems, we see that not all types of uncertainty are equally important. So this problem is a bit more complex and a bit more detailed than we hoped for. We see that, okay, let's consider at this data uncertainty and this model uncertainty and these problems of medical diagnosis and active learning. For medical diagnosis, we care about data being not good enough. So an image is too noisy. There is too small amount of blood on this cycle. And it means that we have high data uncertainty. And for medical diagnosis, it's very important. Model uncertainty is less important because typically we can train a pretty good model using a pretty good sample. And so the story here is about data being not very good. For active learning, the story is very different. I would say it's kind of an opposite one. Because for data uncertainty, it is less important because if we add noisy data, if we add kind of not very noisy data to a sample, it doesn't make much difference. Actually, noisy data, I suppose, even less useful for training. But the main part here, the main question for active learning is to actively learn a model so it acquires more knowledge. And because of this, we are interested in model uncertainty. We are interested in parts of the data where the model is unclear, where the model can acquire new knowledge and become a better version of itself. So there is one issue with uncertainty, like two types. We need to quantify all of them. Kind of. You can project these examples, these considerations onto hallucination detection as well. I wanted to start from like foundation, so you can become kind of more familiar with the problems overall, maybe more interested in this theoretical part. Okay. Another examples here. Okay. Sorry. Another thing here to kind of see how it looks like for toy problems. Let us consider two some two problems and what uncertainty estimation for them could be. So for the regression problem, we want to predict some value of a function. For example, we have a kind of a flat size, and we want to predict the size of this flat to kind of manage and to put it kind of on sale or for rent or rent some apartment. And in this case, we can say that we have these red points. Okay, you can see uncertainty at all. Okay, very uncertain uncertainty here. But okay, so basically we want to draw some uncertainty confidence interval. Who knows what is a confidence interval? Confidence interval? Oh, you can raise your hand. Okay, I know. Okay. Very nice. Thank you. So it's about how kind of big would be the confidence interval. Yes. And so we can say that for regression, we want to do something like this. We want to predict that we are uncertain to this scale. For classification, it's a bit different. We can also create some toy example. So we have orange points, we have blue points of other class. This is blue class 1 and orange class 0. And our uncertainty would be something here, yes. The most uncertainty at the boundary between these two classes. So another example of what uncertainty can look like. Also, we can try to think about it and provide some simple solution. Basically, let us imagine a classifier model that takes an image as an input and outputs probabilities of a class. So it has some black box inside this thing. It has some representation maybe. But what's important is an input image and probabilities that classifier produces. Actually, all the image classifiers produces something like this. A big list of numbers, and for each number we have a kind of probability of a specific class. A probability of a dog, a cat, eye, ear, fox, and so on. So basically we can say that these guys are kind of measure the confidence of the output, yes? If we have here the probability of a cat to be 0.99, it means, okay, we are close to 1, it means we are very confident that there is a cat, and we have very low uncertainty. So basically, we can take the maximum probability from this list and say this is the measure of our confidence, how confident our answers are. If we are talking about uncertainty, we just subtract this number from 1 and say 1 minus this maximum probability is the uncertainty estimate. Okay, and that is one example of how can we provide a pretty good score, a pretty good initial baseline for quantified uncertainty. One problem here is that we don't have this type of distribution of probabilities in the training data. In training data, you have something like this. You have typically a single label for an image. So it all zeros for all classes. It is not a dog, not an eye, not a fox. And one at a single position where we know what is the class of this image. Is this a cat? So it has 1 here and zeros at other places. So we can see that in training data, we have very little examples of how a model should be uncertain. We actually don't learn the model to be uncertain. We don't have these uncertainty scores in the training data. And that's one problem. Okay, we can illustrate it in a slightly different way. So we have a lot of images of clear cats, clear dogs. And we don't have these cat dogs images here. Because, okay, it would be nice to have something to learn that we can be uncertain and how uncertain we should be. But actually, we don't have this orange part in the training data. So basically, we have two challenges to estimate the uncertainty. The first challenge is that we have different types. And we exactly don't know what we aim for. We need to start from the application and design what kind of uncertainty do we need in this specific thing. Like it should be data uncertainty, it should be model uncertainty. Okay, maybe you can invent something, some new type of uncertainty. And the second challenge here is that typically we have a little information about what true uncertainty should be. We have these 0, 1 labels for images, And it basically means that we don't learn the model to be uncertain. And it means that, okay, it's not very easy for a model to learn. And you can project these ideas, the challenges, to LLMs, to hallucination detection as well. Again, we have different types of hallucinations. Sometimes we're more interested in one type, sometimes in some other type. And very hard to construct some universal hallucination detector. And also, we can talk about the unsupervised nature of this model. So each month, a new version of Gemini, of ChatGPT, of DeepSeek appears. You never know what is inside this model. And if you never know what is, okay, at what examples this model does not give right answers, especially if you're not talking about some simple question like what is the capital of Nepal, but about some tricky question, kind of, for example, summarization when you have a large text, you want to make it a small text, and it's very hard to judge. Is it a good output or bad output? And that's the problem, yes? We don't have labeled data for hallucination detector training. And, okay, not an easy thing to do, yes? Okay. Any questions to the moment? Anything? Yes? Can you use the microphone, please? Yeah.
You said it's an unsupervised or semi-supervised learning problem. I mean, are you saying that what type of uncertainty is that kind of a problem, or the challenge comes even more in those unsupervised and semi-supervised?
I think it's more like a problem that we are solving is kind of very close to unsupervised learning because we know little about the true uncertainty labels. We don't have in the training data this type of objects. And because of this, we can't train on them. We can train only of this kind of clear images, but it's not enough. Okay, thank you for the question. And I suppose I'm running out of battery for this guy. It is, I'm not sure, does it work? Not very good, okay. You can think about other questions as well. Yes. Okay. Oh, it's much better. Thank you. So, okay, it was kind of introductory part about uncertainty. And next I want to show you how we can design a certain estimation for simple linear model. It would be nice if you're familiar with calculus, with probability theory, and so on. If it is not, okay, I hope you can try to understand this, or maybe it would motivate you to learn this stuff. So let us consider maybe the simplest possible model for regression. Okay, who knows what is linear regression? Okay, very nice. Thank you a lot for your hands here. So basically it means that we have, what does a linear regression mean? It means that we have some set of features, we have some output, and we have a link function between the input and the output. We think, okay, we need to have some linear coefficients of these input features to predict the final output. That's the idea here, yes? And so by learning a linear regression model, we learn these coefficients theta. So for each kind of feature, we need to quantify how important it is to predict the target variable. Again, let us consider kind of a house price prediction. And this is our output, this is what we want to predict. And we have the size of this house in square feet as an input feature. And in this case, we learn a coefficient that links the size and the total house price, maybe just multiply by the mean price of a square feet in a specific city. And also add some adjustment because I suppose smaller houses are typically more expensive in this way. Also, we typically assume, so this is our kind of basic linear regression model, we actually often see that we don't have not only this linear part, like we just multiply the size by 100 and get the output, but also there is some noise, some information that we don't include in our target variables. This epsilon means that we have some uncontrollable part of the model, some noise that we also can model kind of, for example, it can be Gaussian distribution with zero mean and sigma squared variance. In other words, we also can formulate this in a probabilistic way and say that if we have some vector of features, we know like the mean value of the output, like the expected value. But also we know that there would be some noise, so we have a probabilistic distribution of the target variable given the input x. So for specific x's, we have the mean value and the noise variance for it. So this is what we can try to do. Also, we can get a probabilistic approach for the distribution of parameters as well. Basically, we can say if you have no data, there can be a lot of lines that fit this data because we have no data at all. As long as we start to acquire more data like this, blue points, we can say something about these red lines, about the true functions, the true correspondence between the size of a flat and the price of a flat. And it means that as we have more points here, we have more concentration, more concentrated red lines that should more or less correspond to the data itself. And given this, we can define the distribution of basically this line. So what are the most probable red line that goes kind of better through all these points, and that something like this would be not a very good idea, yes, here, because kind of it contradicts the data we have. So we have the distribution for y, for the target variable, given the input and the parameters, and we have uncertainty about the parameters. And to obtain a final uncertainty, we need to combine them. So for specific uncertainty about parameters, we have uncertainty about the target variable, and we integrate all of this. So we kind of sum up over all the thetas here with some weight. Basically, if you have some very low probability curve, we don't care about it. It doesn't contribute a lot to the uncertainty. But if you have some very probable thing, then yes, we should take into account more. Okay, we can take this integral, long story short, and obtain the final distribution of the predict variable. So it again has the mean value, the prediction, here it is, this guy here, this x, the vector of input variables, multiplied by the vector of parameters, we estimate it. And also we can estimate this second guy, not only the mean, but a variance as well. And it means that now we have this uncertainty estimation. So this variance is something that we are certain about. And you can look at how it looks for some specific one-dimensional example. So again, we have one-dimensional input x, we have output y, and we have these training points here, and we estimate these coefficients, and we see that the kind of confidence interval here is okay, now better. That is narrower here in the middle and wider here, which means that we don't have training data here. Also, in this example, we can decompose model uncertainty and data uncertainty. Data uncertainty is the variance of the initial noise in the data, the noise of the observations. And the model uncertainty is how uncertain we are about the parameters itself, how data can help us to say something about this dependence between the x and y. So, what is good about sync? We solve this problem actually. We obtain some final formula. It's okay if you don't understand this formula, but it's important to understand that we have two parts here, model uncertainty and data uncertainty, and we have specific values we can measure, and that's good. We kind of solve this problem. Okay, it's not very rich specifier, but in neural networks, it would be very different thing. Because we can't actually, in this case, you have this integral, and we can take this integral. For neural networks, we can't do this. We need to use some kind of approximation to make it work for neural networks. We need to apply some engineering tricks. And this thing is even more complex if you are talking about LLMs that are very big, and the output is not a single number, but a big, big text. We need to think about it a lot. So, what we can do? Historically, first approach, historically most fundamental one, is so-called pseudo-Bayesian methods based on deep ensembles. So ensembles, okay, let's explain few words here from this title. Ensemble, okay, so you can create a single machine learning model. If you have many models, it's an ensemble of models. For example, a gradient boosting is an ensemble of what? Typically, decision trees. Yes, we construct many decision trees, we unite them, and now we have an ensemble of decision trees. Okay, sometimes it is not that simple because we have a neural network. We have so-called deep neural network. And so we call this deep ensembles of deep neural networks. Bayesian methods, okay, I will try to show it a bit later. Okay. So again, when we are talking about the distribution of the output here, we have two parts in it. The first part is related to uncertainty about the prediction. And the second part is related to uncertainty about the parameters, the model itself. So we should take this integral, and as I told you, we can take this integral in this case because this is a very complex thing here. So we can instead do this stuff. We can say that instead of looking at all possible parameters, at all possible networks, we can select some number of networks, some ensemble, and unite them in a single thing. It's called Monte Carlo estimate applied to this specific thing, to this specific guy here. So basically we say that we take this theta case, k is index for a neural network, and we have the distribution of the output, these probabilities for dogs, cats, foxes, and we average them over all ensemble members we have, over all neural networks we trained so far. And basically that is the thing that people were doing and that worked pretty well. And I would not say, okay, I skip this guy. I would like to focus here a bit and say that sometimes we can do better when we put different weights to different neural networks, because some networks are better at determining the probabilities and some are less good for this. And we can do this with topological data analysis. So, very natural approach and actually pretty simple to implement. So the algorithm consists of actually like two steps. The first step is very similar to training a common neural network. Yes, we just train not one neural network, but train k capital of them. The second step, just average the predictions and hope it will do better. Pretty similar to the idea of ensembles in regular machine learning. But from this pros come a lot of cons. Like the main one being that now everything is k times more expensive. We need an ensemble here. And for kind of decision trees, it's okay, yes, because each decision tree is a pretty simple model. If you unite all of them, we have also a pretty simple model, pretty easy to train, pretty easy to infer, and so on. For LLM, we have training costs that is tremendous. Like it can take tens of millions of dollars to train a single LLM, like DeepSeek. And this is kind of a lower estimate. If you take into account that you need many runs for training, I can say that, okay, maybe about 100 millions of dollars is something you need to train an LLM from scratch. And now, okay, some guy from your company, from your R&D department comes to you and say, okay, we need not one model, we need to train 10 models. And it means that now we have not $100 million, we need $1 billion of models just to estimate the uncertainty. I suppose, okay, if you are kind of a startup founder, a businessman, you say, okay, why are you doing this kind of? Why should I do this? Maybe there is some simpler approach to make it work, to make it cheaper, to make it kind of more computationally efficient. And actually, that's the thing that many people were thinking about. And later we will, okay, this is what we try to do now. Okay, so we want a single model here instead of an ensemble, and we want also the quality to be high. So let us consider kind of a classification based on a large language model. We have some input text, and we have an answer to some question. Suppose it is a single word as an answer, like for example, you have an option cat, option time, option dog. You select some option here. And similar to what you have in a classifier, in LLMs, you actually have probabilities for the next token stored inside the model, the probability of all the words in the dictionary actually. So it's about like 100 to 200,000, but still it's a big list of number, a big list of number. And we can say that certainty or confidence of our prediction is the probability of the maximum of this token, the maximum probability for the next token we generate. And okay, it's pretty reasonable. Yes, if LLM says the next word is a cat with probability 100, then LLM is very certain about this output. And it means that, okay, this would be a good uncertainty baseline. If for all words the probabilities are almost the same, then the maximum probability would be 1 divided by m, 1 divided by the dictionary size, and it would be something like 1 divided by 100,000, something, okay, I would say 0. So we would be very uncertain of the output, and it then translates to the uncertainty in the answer itself. So it's actually a good baseline. I can advocate more of it, but another evidence that it is good is that it's very hard to design something better actually. If you look through papers on this topic and they say, okay, we are doing this and this stuff, often if you try to reproduce the experiments, it turns out for some reason that this certainty used in this way, largest maximum of PI over all PIs for the dictionary, is the best thing you can do. Also, there is another thing that's very important here. If you have an LLM that you have access to, it's very easy to get these probabilities. You don't need to train any additional model. It is a fully unsupervised method. Maybe you can remember from the first part that one challenge of what we are doing is that we kind of solved an unsupervised problem. Here you have kind of a pretty good model, and you don't need any supervision, any efforts, any additional computations to complete to have this. Also, you can do something a bit more advanced than just the maximum. You can take all the probabilities and compute the entropy of this probability distribution. Actually, it works pretty much the same, a bit better. If you know what is entropy, okay, a good thing for you. If you don't know, okay, in this case, it's not very obligatory things to know. Okay, so I was asking myself a question. Can we do a better thing than this softmax, this is entropy? And actually, yes. We can say that, okay, we already have a pretty strong baseline, this entropy, this maximum probability, but can we slightly fine-tune this model, slightly fine-tune this head, this small part at the top of the model? So we don't fine-tune all LLM, we fine-tune only this small head to make a better prediction of this probability, this uncertainty. And actually, yes, it includes some technical details to complete this fine-tuning. But the main idea here is to just copy weights from the original model, slightly fine-tune model, but not too much, and control that we are not going too far away from the original model by regularizer losses that corresponds to what we are doing, that our prediction is not very different from what we had before. And in this way, we can obtain best results for almost all cases. We actually conduct experiments with small large language models as LLM and just LLM, like regular times like 3 or 7 parameters, like 3 billion to 7 billion of parameters. And all the time it was okay. All the time it was pretty good. And okay, that's one thing. Also, you can ask yourself deep questions. If you are kind of a natural language expert, an engineer here, you can try to think what actually these probabilities of tokens are. So we can go as direction. And actually, it means that sometimes it's not about the choice of meaning, but just choice of the word among synonyms. For example, you generate 3 different responses to the question, what is the capital of France? And both first 2 options are legitimate, yes, Paris and it is Paris. Yes, both kind of correctly answer the question, kind of. You show it to any human and human says, yes, yes, both are right, okay. I score this LLM 100% right, 100% accurate. But actually, when we are doing this probability routine, I explained 2 slides before, it would be a very high entropy because for the first answer, Paris, the probability is 0.5. For the second one, it is 0.4. Yes, here, this number here. It means that we are very uncertain what answer we to choose. Was this uncertainty? Okay, maybe you remember we talked about the type of uncertainty. This is a type of uncertainty that is not about meaning. It's about non-semantic features of the text. So basically, we can try to make it better. And very natural idea here is to unite different answers. So if we feel that the meaning is the same, and we have specific NLI models to do this in NLP, so we cluster them, and now we have clusters of answers, and we have probabilities of a cluster. So we unite Paris, and it is Paris, and now it has very high probability, 0.9, almost 1. For London, okay, what's the same answer here, and it has still low probability, but if we are talking about the semantic clustered max probability, it can improve the solution. It is not as straightforward to implement as I'm saying. You need some tricks to make it work, but overall, it's one example that you need to think better about what you're doing, not just blindly apply the methods. You need to think of what you're actually doing, what uncertainty you're estimating. And this applies not only to uncertainty, but I suppose to overall machine learning. Because often people overlook that what actual problems they're dealing with. Also, this specific method is not very efficient, actually, kind of. I was promising you that it would be a single generation of an LLM to estimate the uncertainty. In this case, it is not like this, because here you need to generate multiple answers and comparison along ones. So we are still on this journey. And also we are kind of going in the direction I was starting from, hallucination detection. Basically it is, okay, let us define it one more time, and one more time speak about the motivation behind this. So there can be many risks related to hallucinations in LLMs. For example, we can lose user trust and he no longer pays for our ChatGPT. Also, when we are taking some decisions based on these LLMs, and if you take the wrong decision, it can cost money or it can cost even life things. Also, about kind of hallucinations, we can say, okay, definitely bad thing. Some about small accuracy of a model. We want our model to be accurate. And again, there can be many examples. Let me show another one here. So Warsaw is kind of a capital of Poland, a country in Eastern Europe. And there is another kind of capital in Central Europe, Berlin in Germany. And so we can have a context, a question, and answer. And you can try to calculate this using the context, and LLM can try to do this. And one example is of hallucination is when it takes the number wrong here. Again, it can hallucinate. Actually, we would be talking about this specific, most of the time, specific pretty simple problem. We have a question, we have a context, and we can get the answer using the context. But for some reason, LLM is doing wrong. It calculates wrong the answer. Again, we will start with less efficient, but maybe more understandable baseline to detect hallucinations. It's called self-check GPT, and I suppose the names speak for itself. The idea is the following. We have LLM, and as I suppose most of you know, the answer would be different if you ask the same question LLM. Yes, you ask one time, one answer you ask the second time. The answer can be close, can be not that close, and so on. So we can collect many answers from a single LLM. And we have some original answer here. Let's call this guy here. And also we have another sampled answer, alternative answers, stochastically produced responses. If you know, kind of, we just change the temperature of the generation. So we generate many different options, many different answers. And we can compare them. We can compare how consistent LLM is. If these answers are very close to each other, then it means that the LLM itself is pretty confident in what is going on. And it means that the probability of hallucination is pretty small. If the answer is not very good matches to each other, it means that LLM kind of is not very confident about it, and there is a high probability of hallucination. Okay, and a small question to the audience: how can we compare how different two answers are? Would you suggest? Any ideas? You have kind of two texts. How can you measure how different they are? Okay, you can raise your hand if you have the answer, because okay. Yeah, kind of. A specific model, yeah, like this. Yeah, semantic similar, yeah. Okay, kind of, there is a specific model in NLP, another small neural network that says how different two texts are. Also, there can be something like Levenstein distance when you compare text word by word, but this is not very efficient when we are talking about large texts. So, we are doing this, we have this mean correspondence, mean similarity between texts, and this is a probability of kind of answer being not hallucination. And again, the problem with this method is that it's not very efficient. Okay, you have a single neural network as the input, a single LLM that outputs these probabilities, but you need to run it like in the paper, the number of generations is 20 for self-check GPT. So you generate 20 answers instead of one. And it becomes 20 times more expensive to use this LLM. Okay, I suppose not all people want to spend so much money to be a bit more confident about what is going on. But anyway, it's one option, and also we can try to make it kind of more delicate. For example, if we generate one answer, it is the same to the first one. Okay, let's not continue and say we are safe, we generated a good thing. If they're a bit different, we can continue, kind of some dynamic approach to do this, and so on. But anyway, let us stick to the problem of creating the most efficient thing we are doing. So we constrain ourselves to the case when we can use only one generation, but on the other side, we can look inside the LLM. As you know, LLM has many layers and many heads instead of it. And it kind of reasons inside itself. You can say that very similar to what's going on in our mind. So you have one neuron, another layer of neurons, and so on and on and on. And to give a good answer in the end, for us, we need to proceed this information with the whole our brain. The same thing is for LLMs. It has a rich internal structure, a lot of information stored inside an LLM. And it means that we can try to use this information generated during answering to our prompt to find out what LLM is thinking about confidence of the answer. The first experiment, at least what I aware about, called the internal state of an LLM knows when it is lying. Okay, I suppose the title says for itself. So we take the internal LLM state and try to construct a model, a classifier that says if it is lying or not, if it is hallucinating or not. So we have a binary classification problem, and internal state is a big vector of numbers. We train this thing on some sample of collected hallucinated and non-hallucinated examples, and we have a pretty good thing. And actually it was much better than the alternatives based close to self-check-GPT of that time. Kind of BERT thing or like few short learning here, with accuracy being for many areas about 0.8% for detecting hallucinations. So basically, if you have a sample of points with hallucination, non-hallucinated things, we can train a classifier using internal states of an LLM. But it is not as easy as you can see, because typically we don't have large samples. We need to think about something more efficient and maybe, again, more insightful features, taking into account what is going on inside the LLM. And one, maybe, in my opinion, one of the top methods to attack hallucinations in a supervised way is the so-called loopback lens that explore the attention map of the text. So inside a specific part of an LLM, you have so-called attention map. Attention map is about how close different tokens are to each other according to LLM itself. So basically on the diagonal here, we have correspondence to this token itself, typically high one, and typically we have high correspondences between something close in meaning. For example, we want to answer some question and we have some context, and this attention map in a perfect word should link to this answer in the prompt. So this is the idea, and let us move one step forward and see how this attention is aggregated in two parts of our thing. So we have of our kind of text. The first part, X, is our prompt. The second part, Y, is our response. We can look at specific token and the response and see how the attention is distributed in it. So at what tokens we look. And we can divide the attention to the prompt by the attention to the prompt plus the attention to the response. And that's we call look-back ratio. How often we look at the prompt here. Naturally, we see that if we look more at the prompt, it means that we will be more confident because we will be using information for the prompt that we should use, because we are talking about context-based answers. So we have all these look-back ratios averaged over response tokens, over all layers of our transformer, of our LLM. And again, we train it to predict a binary label. So we train again a linear classifier on top of these scores. And in this way, we aggregate information more efficiently and obtain higher metrics and higher quality of detection of hallucinations. But still, we have problem because we need actually a large sample to make it work. Because, okay, if we compute the number of all heads in even a moderate sample size LLM, it would be a vector of size about 1,000. And if we are talking about bigger models, it even more. So basically, we have 1,000 coefficients to estimate. And it means that we need about 1,000 of example of hallucinations to make it work. Something we typically don't have. especially for larger models. So we need to maybe focus on something even more concentrated, even more useful in terms of that is saying something about the degeneracy of attention map and how connected are the prompt and the response. And this is actually what we did here. We are saying we again have a question, a prompt, a response, and we measure not as kind of separate attentions here, and connections. We just count how connected is this prompt to the response. So we count how strong are these connections here between them. We aggregate them using topological measure called mTopDiv. And in this way, we see that responses deviate from prompt more significantly if we have a hallucination, okay, from natural reasons, yes, because it no longer relies on facts from the prompt, from the context we have in our text. And because of this, we can do this. Also, again, we have this problem with many heads, and we kind of have a separate attention map for each head here. But we can look at how good are different heads at hallucination detection. Here a picture for two data sets for hallucination detection, RAG-Truth-QA and COCA. And here is the number of layers in, I suppose, Llama 7B model, a model by Meta. 32 layers, and in each layer we have 32 heads, a lot of them. And we can measure the quality of this connectivity scores, this mTopDiv scores, for different heads. For each head, we can measure the usefulness of the score separately. And we see, okay, this intensity of the color means how good the scores are. Like darker is not very useful, lighter is more useful, and I highlighted with this green squares the heads with the highest quality. And actually, it means that it's enough to have like 5 heads that are aware of hallucinations. So only 5 heads to make a decision. And basically, our approach called TOHA, Topological Hallucination Detector, is about selection of these optimal attention heads that correspond to better detection of hallucination by itself, and if aggregated, they as well do this job well. Also, it means that we have a pretty complex structure inside an LLM, because some heads inside it are aware that this head is lying. So basically, we can kind of select this thing. And actually, there are some other works in natural language processing that also link different heads in LLM to different functions. So some are responsible for reasoning, some are responsible for copying text exactly from prompt to response, and on and on and on. And in this way, I suppose we can better understand this big black box, an LLM here. Regarding the inference time, okay, this guy, TOHA, is pretty similar to what have been told before, pretty similar to the inference time, actually, yes, about 2 times more expensive. Also, regarding how many samples we need to select these heads, actually about 100. Not, I suppose, not a very big number. So we are safe. We just collect 100 hallucination examples, select heads on top of them. We don't train anything. We just use courses for these heads. And that's it. So we kind of discussed what we need, and we kind of obtained it, this thing. We were looking for fast and transferable approaches, so it works efficiently, does not require additional generation by LLMs, transfers to other datasets, so the quality of transfer would be pretty good, and also doesn't require a big dataset to annotate here. So the TOHA is exactly like this. And maybe the last thing I wanted to talk to you separately is, okay, actually kind of maybe I want to conclude a bit about hallucination detection overall, is that it's still an active area of research, and many people are thinking about how to do better and discussing what is possible, what is not possible for different hallucination types. and actually it helps us to understand LLMs better. And I hope that kind of this problem would be mitigated to some extent using this type of methods. But another approach is not about detection, but rather about how can we train the model to be a better worker for the specific tasks we are interested in. How can we make it a better version of itself? Here I would consider not kind of a big model fine-tuning. To be honest, because I can do this on my own laptop and on my own server with only 5 GPUs. We are considering something smaller. We have a small model, but we want this model to be an expert in one specific domain. It's relevant not only because, okay, this is what I can afford and I can't afford to train kind of Llama 2 from scratch, but also because there is a need to put a model on a phone. We want it to run offline here on your phone that don't need kind of access to the internet or can generate fast answers cheaper because it does not use the GPU resources on the cloud server. So a small model, we fine-tune it, and also we can do so-called distillation. We can take a big model and we can input the required part of the knowledge from a big model into a small model to make it more proficient for some specific domain. We can do it kind of in a general way. We can take all the corpus of the text we use to train a big model. We can also try to use this big model for distillation, like, for example, saying what is good and what is bad, and like making the generated probabilities of the small model close to the probabilities of big model. It is a very long process. It requires a lot of fine-tuning, not very efficient. And there is one idea on how can we do better. We can try to think about more active strategy to train the model. We want to train on the domains such that for these domains we don't have enough knowledge. So maybe we know about the medicine a lot, so we no longer train on the medicine data. We train on programming data because it's not very good here, and so on. So the idea is to focus on narrow domains that we feel that we don't have enough knowledge. In this case, we look at the best possible answer provided by a large model and rank all the domains by saying what is the gap between our model and the large model for this domain, and selecting domains such that for these domains, this model is not good enough. It is actually has some issue with this approach because for sometimes a small model can't do this at all. For example, we have a complex math problem like, I don't know, Fermat theorem proof. And a small model like 3 billion parameters is just not good enough for this. So basically, when we're thinking about this, maybe we can do it even more efficient. And also with a deeper help from a big model. So this is what we actually did, and this paper accepted at YACL 2 days ago. So we again have some training data, but then we proceed a step with ranking all the data with how hard these questions are. So you have regular questions, not that hard for a specific model, and hard questions a model is very uncertain about. And so for regular questions, we can just run supervised fine-tuning, a simple procedure, or even avoid this because model already knows this. But for hard thing, we can use the power of a richer model. We take a big reasoning model, generate reasoning steps for it, so we augment the original question with the required knowledge to learn it. And in this way, we add this distilled reasoning from teacher LLM to train a model, and finally, we supervised fine-tune with all this collected data. And because we focus more on the specific hard questions, we are able to make a better thing. For threat estimation, we actually use something as simple as entropy here, and just say that, okay, we have this long tail with hard questions. And actually, it allows us to make a better model with like 3 times lower cost, because we don't distill on supervised fair tuning for like data of regular complexity. So, to conclude, hallucination detection problem is something very serious we should take into account. It's so much. It is not as maybe as bad as we think in typical scenarios, because all models have errors. It's okay to have errors. But in some critical safety areas, we can do better. We can try to create a guardrails, a hallucination detector approaches. And from the design of the problem, it appears that it should be able to learn faster this detector and using some small data samples. And actually, for now, the best approaches come from 2 ideas. The first idea is to look at the specific parts of the internal states on how the attention is distributed inside the model. Or the second option is to use multiple runs for some model and compare the answers. If the answers are diverse, that a model not very certain about it. Also, please see that in both options, we use a single model here. We don't use something bigger. Regarding specific internal states, specific information about internal states, we found out that the connectivity provided by the topological data analysis in this internal states is a good signal for hallucination. If response of a model is not connected to the prompt, it means that we ignore the context from the prompt, and with high probability we would have a hallucination. And again, still with this context, we still observe a lot of hallucinations. Also, when we are talking about not detecting hallucination, but on a proven model, we also can use uncertainty estimation or hallucination probability. Just this is a signal that we should focus on something the model does not know yet. So we need to put it inside as hard and push as hard as we can to make the model learn it. You can look at this. It's a kind of a lot of papers here. 2 my papers are kind of a top right corner. Also, if you are interested in kind of my laboratory or in Skoltech in general, you can go and check pages with PhD and master programs there. That's all for me. Thank you a lot for your attention. Yes, I suppose there are some questions, and I hope someone can bring micro to the people who are raising hands. Yeah, maybe if you can stand up, maybe.
Thank you, Professor, for the lecture. I have one generic question related to LLMs. It is now being told that only scalability doesn't help to build us the general intelligent LLMs. So, is there any work being done to make the LLMs agentic internally rather than through context? And how can we incorporate agentic attributes in the base LLMs rather than memorize the facts?
Can you please repeat the last sentence? Sorry.
Yeah, the main question is, has there been any work to make the base LLM agentic internally rather than through the context?
Yes, we can detect hallucinations of different types. And also it's interesting that we can collect kind of different samples. One example of other problem that's pretty important and that is interesting to solve is long context or long tail, questions when you want to look at specific small piece of knowledge that typically not learned by a big LLM, but okay, that we can need for some application. Okay, if it does not answer the question, you can come to me after that.
Okay, thank you, Professor. I really enjoyed the session. So I was curious to know what's the distinction between model not knowing something versus hallucinating? What's the better line, to draw the line clearly?
Okay, it's not an easy question, a deep one. It's something kind of not all of scientists know. Actually, when we are looking at the papers, I suppose that should be some. Do I have it? Almost all the papers in hallucination detection, they report so-called Rockawg scores. It means they don't care about the specific threshold. It just reports on kind of how good the score is distinguishing. When we're talking about specific score, specific thresholds for a score, I suppose right now it should be kind of selected based on kind of, for example, F1 measure, and maybe on some business-oriented metric, because, okay, we don't want the model to be kind of, to make a lot of errors, but we also don't want model to abstain from answers a lot of time, yes? So we need to find a compromise, and I suppose it would depend on kind of specific application. For example, in medicine, we can cut off almost everything we are not certain. In kind of regular questions, like, I don't know, what is the population of Kathmandu? Okay, I suppose if you kind of have some errors, not a big deal. Any other questions? Okay, I suppose that's all. If you have any other questions, I will be here at the sofa after the lecture. Thank you a lot for coming today and listening.